determinant of a matrix is a very important entity. It's just one number coming out of a large number of numbers, which is what a matrix is. But this one number contains as much information as possible for one number to contain about a table of numbers. So that's what a determinant is. Let's take a look at how it is defined and what it can do for you. First of all, it's defined only for square matrices. And there are different notations for it. A delta for determinant or single vertical bars. And that's what we will use in our book and in my slides. So like I said, it's just one number, but it contains a lot of information about the matrix. It's a function of the elements of the matrix. So all we can say at this point is that if A contains elements aij, n by n matrix, so n square of them, then determinant of A is a function of all these n square numbers. If you think of A as a transformation, in this case, A is a square matrix, so it's transforming vectors in one Rn to another vector in another Rn, or you can even think of it as transforming the vectors from one space to itself. Now, what I can tell you right away is that if the determinant is non-zero, then the transformation is reversible. So determinant is kind of like the size of the transformation. If the size is 0, then you cannot invert the transformation. It's like multiplying a number with 0. If I tell you 0x is say 5, then you cannot figure out what x is because x is 5 by 0. It can be anything. So if determinant of A is non-zero, then we can say that there is an inverse of A that reverses the operation. In other words, determinant of A not being equal to 0 is the necessary and sufficient condition for A inverse to exist. If determinant of A is 0, then A inverse cannot exist. Determinant of A not equal to 0 implies and is implied by A inverse exists. In other words, if there is an inverse, then the determinant cannot be 0. If determinant is not 0, then there is an inverse. So the test for singularity is just the computation of the determinant. One test for singularity is just that. If determinant is actually 0, then we will say that a singular is non-invertible, is degenerate. So there is an algebraic interpretation of the determinant, and it's that if the determinant of A is not 0, then the system of equations Ax equal to B can be solved uniquely, meaning there's only a unique solution for the variables in the variable vector x, and we can find A inverse, at least in principle. So this is something that we wrote earlier. Ax equal to B implies that A inverse A times x is A inverse B, providing that A inverse exists, and that condition will be satisfied if the determinant is non-zero. So x is A inverse B. I'm multiplying the left-hand side and the right-hand side on the left with A inverse, and A inverse A is of course I, always providing that A inverse exists. Then I times anything is just that anything. So x becomes A inverse B, and that is the solution. This looks like you're dividing by A, but on the left. So you can write this B getting divided by A on the left. This notation is actually used in some programming languages specific to linear algebra, such as MATLAB and Sage Math, etc. So if you actually write, if you provide a square matrix A that has an inverse and write for some vector B, A backslash B, it'll actually spit out the solution. Once again, the existence of non-zero determinant is the necessary and sufficient condition for unique solutions, and of course for the existence of A inverse also. So as she can see, the determinant of the matrix has something to say about the solvability of the system of linear equations that it represents. There is also a kind of geometric interpretation of determinants. Let's take a simple example in R2, 2 dimensions, so that we can actually draw pictures and visualize it, and then we'll try to extend it to multiple dimensions. If you have a transformation A and you take unit vectors and apply the transformation to the unit vectors, what will happen? So suppose we have A, the 2 by 2 matrix, so we can multiply that with 1, 0, and now we can use the column piece from matrix multiplication, which says that is a linear combination of the columns of A, as you see here. What type of linear combination? 1 times this, 0 times that. That means just this, and that is AB. So the first unit vector will just pick out the first column of A. Similarly, the second unit vector will pick out the second column of A. That's what I said there. A maps the first unit vector to its first column and the second unit vector to its second column. So if you have a unit square, then you can convince yourself that it's going to get mapped to the vertices 0, 0, because 0, 0 doesn't move. 1, 0 will become AB. 1, 1 will become CD. And this 1, 1 will become the sum of those two. And that is A plus C, B plus D. So that's what's going to happen. And after having done this, I can look at this and I can see that this is a parallelogram. And determinant of A is the signed area of this parallelogram. What does the sign mean? We'll come to that in a second, but for now let's ignore the sign and just say that it's the area of the parallelogram. So if you take the first unit vector, that gets transformed to the first column of A, and the second unit vector goes to the second column of A, and those are the ones that I have in brighter red or brighter blue. Then I goes to that parallelogram, and determinant of A is actually the area of that golden parallelogram, and that turns out to be AD minus BC, which is almost too good to be true. You will see why that is true in a second. So the definition of determinant of A in R 2 by 2 is something that you have to remember. A is AB and CD standing side by side, and in that case the determinant is AD minus BC. AD minus BC. Now determinant can be positive or negative because AD can be more or less than BC. Forget about the meaning of the sign for now, and the magnitude of the area of the parallelogram is actually going to be the magnitude of AD minus BC. That is something that we will see using this fancy picture. So I have the parallelogram to which the unit square transforms, and that is that parallelogram. So that is what you start with. Now let's consider a rectangle with side A along the x-axis and the D along the y-axis. So the area there is AD. And let's consider another little rectangle there, the green one, with side C and B. So you can see that that side is B, the vertical side, and the horizontal side is C. Now, what I'm claiming is that the area of the red parallelogram is the same as the area of the blue rectangle minus the area of the green rectangle. To see that, you can immediately see that that little wedge there is the same as the little wedge on top of the green rectangle. What I'm trying to do is to chip away from the blue rectangle some parts so that I end up with the red parallelogram. So I chipped away that, then I chip away this little guy, then I see that yellow region, I move it to the other side so that I get closer to the red parallelogram, and then I see the blue region, I move it up there. Now I see that I have done too much. That green region is actually the sum of the blue and yellow regions, and that has to be subtracted. After doing all that, you can see that the area of the parallelogram, area is what I mean by this notation here, the size of that parallelogram is the area of the blue rectangle minus the area of the green rectangle. This was something that I came across on the web with the title that said proof without words. So I just had this diagram and said this is it. This is the proof that the determinant is actually AD minus BC. So I stared at it for some time and then I convinced myself that this is actually true. So I am expecting at least some of you to stare at it for a minute or two and understand that this is actually true. Let's do this once more. So what I'm claiming is that the blue guy minus the green guy is AD minus BC, which is true because the area here is AD, the area here is BC. That is obvious. But what's less obvious is that that's the same, the area of the parallelogram. Let's continue. Let's try to construct the parallelogram out of these two rectangles. So what's the first thing that I need to do? I have to move that guy over to the top so that I get closer to the parallelogram. Then I chip away that little wedge, the olive green wedge, then the silver wedge. Now what do I have in my green rectangle here? I have filled it up. So if I subtract away the green rectangle from the blue rectangle, what I will end up will be the area of that parallelogram, but that's not the parallelogram that we're looking for. There's one more little region that we have to move to the right hand side, that is the yellow region. When that moves, we have actually ended up with the red parallelogram, and now because all the little pieces match, the area of that guy is the same as the area of the blue rectangle minus the green rectangle. So if you haven't completely caught that, just watch this little piece of the video once more and that will be obvious to you. It's just that each one of these pieces that you have, this guy and this guy, can be moved either to here or here, and then what's left over here is the same as that, and what's left over here is the same as that. You will understand that. Now, we ignored the sign of the determinant. Let's get back to it now. The determinant is considered the signed area in R2, or it is a signed volume in R3 or Rn, signed hypervolume. The sign comes from the order in which the vectors and their transformed versions appear. Again, our original transformation using A, C, B, D. The first unit vector gets mapped to AB, the second unit vector gets mapped to CD. And if they are in the same order as the unit vectors, I'll explain to you in a second what that means, then the sign is positive. If they have to flip, then the sign is negative. So let me tell you what that means. So let's look at this example matrix. I have my unit square there, size 1 by 1. So my red vector is my first unit vector. The blue vector is the second unit vector. Now, the first unit vector, 1, 0, will go to 2, 1. So that's the bright red vector. Then the second unit vector will go to 2, 2. That is my bright blue vector. And now let's look at these two transformed vectors. Now, originally, my blue unit vector was to the left of my red vector. So if I use my fingers to go from the red vector to the blue vector, the unit vector, then it's going to go in counterclockwise direction. And let's look at the transformed versions. Again, the transformed blue vector is on the left of the transformed red vector. Again, I have to use a counterclockwise direction to go from the red vector to the blue vector, the transformed versions. So that is considered positive. Now, the determinant as you computed there is 2 times 2 minus 1 times 2, that is 2, that is positive. So to put that in words of single syllable, blue unit vector is to the left of the red one, and blue transform vector also is to the left of the red one. So the determinant is positive. Now let's take another example. Here I have 2, 1 and 4, 2. So 1, 0 goes to 2, 1 as before. 0, 1 goes to 4, 2. Now if you look at the transformed vectors, they seem to fall on top of each other. Now let's look at the determinant. The determinant is 2 times 2 minus 1 times 4, that is 0. That is understandable because the area of the transformed parallelogram has collapsed into a line, so the area is 0. So that's what it means to say that the determinant is 0. The area of the parallelogram is 0. Fine. The blue unit vector is to the left of the red unit vector, but the blue transform vector is on top of the red transform vector. It's neither to the left nor to the right. So the determinant is actually 0. Now one more example. I have 2, 2 and 2, 1 as the columns of A, and my red unit vector goes to the bright red vector 2, 2. My blue unit vector goes to bright blue vector 2, 1. As you can see, it crossed over the transform vector. Again, if I look at how I would get from my red unit vector to the blue vector, I have to go in the clockwise direction using my fingers. If I were to go from the transformed red vector to the transformed blue vector, I have to go in the opposite direction. So the thumb was pointing this way for the unit vectors, is pointing the opposite direction, going into the page for the transformed one. And that's when we have a negative sign. And as you can see from the determinant computation here, 2 times 1 times 2 times 2, that is minus 2. And that is the area of that parallelogram with the associated sign. So the blue unit vector is still to the left of the red one, but the blue transform vector now has moved on to the right of the red transform vector, and the determinant is negative. That is what it means. So if one vector, when transformed, has to cross over the other vector, when transforming unit vectors, of course, then the determinant will flip sign. Moving on to a 3 by 3 matrix, we define its determinant in terms of 2 by 2 subdeterminants within. Let me explain. So determinant of A, where A has 3 columns and 3 rows, one way of computing that would be to take the first element A11, delete the corresponding column and row, then get the subdeterminant here. That's a 2 by 2 determinant, which we know how to compute. Then minus, there's a minus there, A21, again delete that guy and the corresponding row. Then you get a 2 by 2 determinant comprising these 4 elements, and that we know how to compute. Then you move on to A13, delete that column and that row, you get a 2 by 2 determinant there and compute that. And this is the way it is done. So since we know how to do determinants for 2 by 2 matrices, we can define the 3 by 3 matrix determinant using the 2 by 2 one in a recursive kind of fashion. Now, the first term comes with a positive sign, the second one with a negative sign, then positive. There is a method to this madness that you will understand in the next slide. But here what we have done is to expand the determinant over the first row. You could do that over the second row or the third row or any column, and that is possible. And that's the way a higher order determinant works. Now, if you want to move on to a 4 by 4 matrix, you will do the same thing. First, define it using determinants of 3 by 3, the submatrices, and then each one of the 3 by 3 will become 2 by 2 determinants of the submatrices within, and that's how it will go. Obviously, as you can see, there's so many computations, so there's a horrible numerical computation that's going to happen when you want to compute the determinant. Geometrically, the determinant in R3 is a volume of a parallelepiped. It's a signed volume. The sign comes about depending on whether one of the unit vectors, when transformed, has crossed over to the other side of the corresponding transformed unit vector in another direction. Now this, in order to make sense of it, in order to actually write it down mathematically as a formula, we have to define a couple of terms. Let me define something called a minor and a cofactor. What we wrote in the previous slide using colors now is A11 and a subdeterminant, then A12 and a blue subdeterminant, and a black one after that. So the first one has a determinant of a submatrix. In order to get the submatrix, you remove the first column and the first row because you are taking the first row, first column element. So the column and row corresponding to that element you delete, and then you get a smaller matrix and you compute the determinant of that guy. So that subdeterminant, the red one in this case, is called the minor of the corresponding element. It's a subdeterminant that is called the minor. It's not the matrix. Matrix is just a submatrix, but the determinant of that submatrix is called the minor. There's a determinant. So keep that in mind. So we can use M11. So to put that down in black and white, Mij is the determinant of the submatrix without the ith row and the jth column of the original matrix. And this goes even if it is a 4 by 4, 5 by 5, n by n matrix. It's not merely for 3 by 3 matrices. Now the second term has a negative sign, so the blue minor is negative. And if you absorb the sign into the minor, in other words, you consider the signed minor, that is a cofactor. So cofactor of A11 is just the red guy. Cofactor of A12, on the other hand, is minus this blue guy. And how do you get the sign of the cofactor? Sign is determined by minus 1 to the power I plus j. So let's do that for A11. What's 1 plus 1? That is 2. What is minus 1 to the power 2? That is 1. So that comes with a positive sign. So what's the second one that we're considering? It is 1, 2. What's 1 plus 2? That is 3. What is minus 1 to the power 3? That is minus 1. So the blue minor comes with a negative sign. So the cofactor for A12 has a negative sign. You can actually find the sign of the cofactor for any element anywhere in any big matrix. You just look at the row number, column number, add them up, minus 1 to the power of that number, and that would be the sign. So that lets you expand on not merely the first row, any row or column. Let's say this column is the one that you want to expand on. The first term in the expansion will be A12 times the minor and there's an associated sign. This is 1 and 2, so 1 plus 2, so that has to be minus. So it will be minus 1 times A12 times the determinant of A21, A23, A31, A33. So that's the idea. So this expansion is called Laplace formula for determinant. So it uses the minors and cofactors. You can write it down as a formula. It's a compact formula. It's not very complicated as a mathematical formula. So it just says that the determinant of A of an n by n matrix this time is minus 1 to the power I plus j, Aij times its minor. So minus 1 to the power row number plus column number. This is the row, this is the column, and you're multiplying that with the minor, and then you're summing over j. You can actually do that for any row or column. Now, since we said that this sign times the minor is actually the cofactor, so we can write it even more compactly like this. And if you look at it this way, it looks like a compact formula. You can implement it using some nested for loops in a program, but don't do that because it is recursive and it's very, very expensive computationally. You can sit down and calculate the computational complexity of this one. I would invite you to do that as an exercise, and it is not pretty. And again, in Rn, determinant of A is assigned hyper volume of the hyper-parallelepiped in n dimension. So here is an example. So it's a 4 by 4 matrix. I'm expanding over the first row. So in order to expand it over the first row, the first element is 7. First element meaning the first row, first column, that is 7. So 7 comes out, and its minor is determined by deleting the corresponding row and column in red, and then the rest of it that you see in red here, the determinant is the minor, not the matrix, it's the determinant that is the minor. Then for the next term, you delete the blue guys, the blue column and blue row, and then you get the blue minor here with a minus 1, because it's minus 1 to the power 1 plus 2, 3, so minus. The next one is the green one, that comes with a positive sign, and the last one again comes with a negative sign, that's a yellow one. So delete the yellow row and the yellow column and minus, because that is row number 1 and column number 4. 1 plus 4 is 5. So minus 1 to the power 5. And after that, you have to do the same kind of expansion for that. And then finally, you will get a 2 by 2 in there, which you know how to expand. So this is how it works. And that is computationally very, very expensive. Now, having defined a determinant and how to compute it, now we can look at the properties of determinants. Maybe the properties itself will tell you how to do determinants in a smaller way.